Assalamu alaikum. Welcome to lecture 11 of data mining. So today we have already actually finished the FP growth algorithm. Today I'll just wrap up with a few comments on the FP growth algorithm, and then we will move on to sequential pattern mining and discuss one algorithm in that category, which is very similar to the a priori algorithm. The algorithm, of course, is called the generalized sequential pattern, or GSP. Uh, Actually, before that, we'll also briefly talk about max pattern and close pattern, which are a concept in item set mining. And if we have time after that, we will talk about interestingness measures for association mining. And so that would, I think, probably bring us to the end of this session today. On the next Tuesday, we will probably wrap up this chapter. Maybe we might have one more lecture, maybe, because we still have some additional topics to discuss regarding extensions of the item set mining approach to other types of data sets and settings, as well as there is a subsection on constraint-based mining, which is quite interesting and relevant. So we'll discuss that as well. So maybe 1 or 1.5 session after this one. All right. So are there any questions? Any questions? So we were discussing the FP growth algo, and the FP growth algorithm uses some concepts which make it scalable as well as efficient. And some of those concepts, of course, are the algorithmic approach of divide and conquer, and then, of course, the algorithmic approach of depth first item set generation. Secondly, it does not follow the candidate and test approach, which is used by a priori. And remember when we talked about the generation, candidate generation and tests, so this was kind of tedious. So you had oftentimes had a lot of candidates that were generated. So you then had to do a lot of bookkeeping and scanning of the database to count those candidates. So in the FP growth algorithm, there is no such thing. Basically, item sets have grown from smaller sizes to larger sizes, and their counts are automatically determined based on their counts in partitions of the database. So partition database is another concept that this one uses. Partitioned database, which in the context of FP growth is also known as a conditional pattern base. When you don't include the item on which you project a database, you call it the conditional pattern base. And of course, it uses compression using the FP tree. So these are some of the ideas that it uses. Of course, this compression is based on the tree structure as well as the frequency decreasing order of items in item sets. Okay. So this was the reason why we got to, the high degree of compression. So a couple of things more, and before we wrap this up. So remember talking about the frequency decreasing order. So let's say the frequency decreasing order for any point in time in the recursion is C, D, A, E, meaning that E has the lowest count but is still frequent. And then we have A, and then D, and then C. So if you now further partition this database using E, the lowest count item, so you will find all the transactions in this database that contain E. Since E is the least frequent item, so you will always get prefixes to this E, or you will get prefixes to this item E. So E would usually be at the end of um, that item set sequence. So once you have mined all the item sets that end with E, you then move to the next level, which is in the case you mine with A. So now you will find all item sets that end with A in frequency descending order. So again, this would uh, this would not break the sequence that you had obtained through E. So for example, there might be, let's say in E, so you might have found some transaction, let's say CE, for example, or maybe C, uh, what's happening? Just a second. So E, so let's say you have found the pattern CE and maybe CBE, for example. So E would always be a, you can say, suffix, and you will have some prefix to it. And when you move on to A, you would probably find patterns that has A as a suffix. So for example, you might be able to find for something like CBEA. So there might be E there, but E may not be at the end. Okay. I think that's probably not correct. You will never find any that has E in it. So whenever because we are going from the least frequent item, so you'll find all frequent patterns that contain E. And then when you go to A, so you'll only find prefixes that do not have E in them. And of course, they will have an A, which is usually be a suffix. And similarly, you move on to the higher frequency order until you reach C. So of course, when you reach C, C would be the most frequently occurring single item, and you go into its database and find any other item sets that co-occur with C frequently, and you will obviously form longer item sets from that. So the point that I wanted to highlight here is that you're starting from the smallest or the least frequent item set. Once you have started from the least frequent item set, you will find all item set that contain that. And then when you move to the next, it will not contain that least frequent item set. It only contain the higher frequent item set because you've already done frequency descending order. So in other words, you never break a long sequence when you are starting with the least frequent item set, then move on to the next, and then move on to the next, and then move on to the most frequent item set. So that's one thing. The other thing, of course, is there is recursion uh, because you do E, and let's say you get a database that does not yield a tree that has a single path. So you have to assume that you have to find the F list for that and do recurse it until you find a tree with a single path. So there are actually two conditions. If you get a tree with a single path, you can generate all the combinations and append uh, the projected item set to it. So you'll get all the item sets with that. But if you do not get a FP tree with a single path, you have to recurse until you get FP tree with a single path or null. So that's where you end and then you move back into the recursion tree. So So the FP tree structure that is used in the FP tree algorithm is complete from the perspective of item set mining. So it does not contain information of infrequent item sets. It contains all information that is necessary to find frequent item sets. That's the meaning of completeness. And so the other main property is compactness, and this is because of the ordering, frequency ordering. So the more frequently occurring items usually appear near the top of the tree, and they will be repeated. And simply they will have a counter whose value will be increased. So you won't have to save that path or item multiple times. It will be just saved once. So generally, the FP tree would never be larger than the original transactional database. And in some practical experiment, they have found that you can even get up to 100 times compression uh, using the FP tree structure for item set mining. So we have already discussed this. So this is a basic idea and a general algorithm for the FP tree growth, FP growth algorithm. So let's move forward. So I will skip this because this is something that we have not done, although it's a simple idea. Skip this as well. So if you compare the FP growth algorithm with the a priori algorithm, so in this graph, you on the x-axis is your minimum support threshold, and on the y-axis the runtime. And you have two lines shown here. One is for the FP growth, and the other is a priori. So you notice that the computational time required by FP growth and a priori are relatively similar when the threshold is large. So what does that mean? If the threshold is large, meaning let's say theta or minimum support is 50%. So you are looking for only very frequent item sets. So meaning that the number of item sets would be very small. So if the number of item sets is very small, both a priori and FP growth in terms of computational time are almost identical. But if you reduce theta, which implies that you will find lots and lots of frequent item sets, FP growth algorithm does much better than a priori algorithm. A priori algorithm's complexity explodes as theta reduces, while of course FP growth also explodes, but at a much lower value of theta. So, so FP growth as it is can manage larger uh, item sets much better, and it can handle smaller values of theta as compared to the a priori algorithm. So I will skip this because tree projection as such we have not discussed. So finally, just to conclude, what are the advantages of the pattern growth approach? So of course, it's divide and conquer. So you are working on smaller portions of the data set. So no candidate generation and test, which is always tedious. You have a compressed database, in this case the FP tree, And of course, if we assume the FP tree fits into memory, then you don't have repeated scans of the database, which again is time consuming because the transactional database can be very large. And also, of course, like in a priori, we'll have to do pattern search and matching. So that essentially is also not required in the FP growth algorithm. So you will find implementations of FP growth in various uh, you can say toolkits. So you can do a Google search and find them. One of the older ones is listed here. So okay. So let's now. So we will not discuss further improvement of the FP growth algorithm. So that is because there are lots of improvements and there are still papers that are coming out on improving the performance of various algorithms for frequent pattern mining. All right. Okay. So now let me introduce two more concepts. And the motivation behind these two concepts is that you can get tons and lots of item sets that are frequent. So trying to understand or even uh, record those item sets might be tedious. So what I'm trying to say is, let's say if you run a frequent item set mining problem, let's say the market basket analysis, and you specify a theta or minimum support, let's say is 2%, let's say. So you might get hundreds and thousands of item sets as frequent. Okay? So this is a huge number. So every item that is frequent will be shown from item 1 set to 2 sets to 3 sets and so on. Okay? So you will have lots of item sets that are recorded and that will be displayed. So some of that information might be redundant and you may not find all of them interesting. So one way of kind of reducing, or two ways of reducing this set of generated frequent item sets, is the concept of closed item sets and max item sets. So what is a closed item set? So let's first talk about closed. So the definition is basically, let's say if I talk about an item set X. So X is closed if it is frequent. Okay? Meaning that one condition, of course, it has to be frequent, which is what we typically find from a FP growth or a priori algorithm. And then further, we say that there exists no super item set Y that has the same support as X. Okay? So in other words, and we'll see a simple example shortly, but in other words, let's say we know that AB is frequent. And let's say support is, let's say 5. Okay? So what are its supersets? So there could be various supersets. So let's say A, B, C is a superset. And let's say minimum support count is, let's say 3, let's say. So ABC is, let's say 4, which means that it's frequent. Let's say ABE is also 4, which is also frequent. Okay? And let's say we have ABC and ABE. And let's say we have ABD, which is, let's say 2, which is not frequent. Okay? Of course, so if you look at now this definition, So AB, is AB a closed pattern? First of all, we say look at whether AB is frequent. Yes, it is frequent. Good. So one condition is satisfied. And then the second condition is there exists no super pattern of AB which has the same support as AB. There exists no super pattern. So you notice here that ABC has a support of 4, ABE has a support of again 4, and then we have a support of 3. So there is no super pattern that has the same support as 5. Okay? So in that case, then AB is a closed pattern. Meaning that it may have super pattern that are frequent, but their frequency count is strictly less than the frequency count of AB. Okay? So if, for example, we had this 5 here, then AB would not be a closed pattern because it then had a super pattern ABC with the same support. Okay? So let's now again look at the second definition, then come back to the difference between the two. So max pattern. So X is frequent, that's the same, and there exists no frequent super pattern of X. Okay? So in a way, this is a stricter condition. In the first case, we said that there exists no super pattern with the same support. So it could have a support which is less than this one, but it might be frequent. Here we say that there is no super pattern which is frequent. Okay? So in the example above, AB is frequent. It satisfies the first condition. And let's say minimum support count is 2, or let's say 3. Okay? So the second condition is there exists no super pattern of AB that is frequent, which is false in this case because AB has a super pattern ABC which is frequent and ABD which is frequent. So AB would not be a max pattern. AB, of course, is a closed pattern, but it's not a max pattern. So as I said, max pattern's condition is stricter than the condition for closed pattern. All right. So in general, let's say if C is the set of all closed patterns and M is the set of all max patterns, then in general M would be a subset, or maybe even at the limit case equal to C, max pattern, and then of course this would be a subset or equal to the set of all frequent patterns. So is this point clear? So in general, the set of item sets that you have in M would be less than the set of item sets in C and less than the set of item set in F. Okay. So generally, instead of generating all item sets in F, we generate, or I should say that we generate either C or M directly. So instead of generating F, we generate only M or C. And there are some extensions to the a priori algorithm as well as the FP growth algorithm that would help you find M and C directly rather than all frequent item set, which is F. Okay? So we are not discussing those algorithms. We are just discussing the concept. Okay? And generally it's said that C is a you can say complete representation of F, meaning that if you have found C, from C you can infer all the missing item sets in F. So it's a complete set. And of course, since you're only keeping a few item sets, it covers less space, and for humans to look at them, it's easier for them. Okay. Any questions here? So close pattern and max patterns are shown in the start of these slides. So there is another example here that you can look into. I think it's on this slide. So let's say you have a very small transactional database with just two transactions. The first transaction has items I1 to I100. In other words, item set of length 100. The second transaction has an item set, the same item set 1 to 50. So just two transactions, one has 100 items, the other has 50 items. And let's say minimum support count is 1. So what is a set of closed item sets? So what is a closed item set? The item set must be frequent. For an item set to be frequent, it has to have a count of 1. So, and secondly, it should not have a super item set with the same support. So if you look at this example, item set 1 to 50, the complete item set, I1 to I50, has a support of 2. But any superset of this, let's say if I add 51 into it, that only occurs once. So it means that there is no superset of this item set from 1 to 50 which has the same count. So it means that I1 to I50 is a max pattern. So if you take any other pattern, for example, I1 to I10, it has a count of 2, but there is a super pattern I10 to I11 which has a count of 1. So it's not a max pattern. Sorry, close pattern. Okay? It's not a close pattern. And similarly, if you look at the items set from I1 to I100, it has a count of 1. Is there any super pattern of that which has the same support? There is no super pattern of that. So that's why that is also a closed pattern. So if you look at the max side, I1 to I50 has a count of 2. Sorry, I1 to I50 has a count of 2, and it has a super pattern which has a count of 1, which is also frequent. So it cannot be a max pattern. So only max pattern remains is I1 to I100. So someone has a question?
Sir, can you go to previous slide about max side pattern definition?
Acha. Yeah. So this is the definition that I actually wrote down earlier.
There isn't close pattern and max pattern same thing?
No,
फर्क
it's
क्या
not
है?
the same thing. Uh, the definition is different. The first condition is same. So X is frequent. And secondly, X, there should be no super pattern of X that has the same support, which is close pattern. And for max pattern, there is no super pattern of X that is frequent. ठीक है ना? तो in other words, मतलब ये max pattern की condition, second condition stricter है. So let's say जैसे मैंने पहले भी कहा था कि let's say minimum support मुझे support count जो है वो 3 है. तो मेरे पास so 4 भी frequent होगा, 5 भी frequent होगा. So let's say किसी का super pattern है जिसका count 4 है और खुद ही वो 5 है, ठीक है? तो वो close pattern तो हो सकता है, but वो max pattern नहीं होगा. ठीक है?
Okay.
बिकॉज मैक्स पैटर्न क्यों नहीं होगा, बट 4 वाला भी फ्रीक्वेंट है, बट मैक्स क्लोज पैटर्न वो हो सकता है, बिकॉज क्लोज पैटर्न में ये कहता है सिर्फ 5 काउंट नहीं होना चाहिए, 5 से कम कुछ भी हो सकता है. सो एज आई सेड बिफोर, मैक्स पैटर्न का जो सेट ऑफ आइटम्स है वो थोड़े होंगे इन जनरल. ऑफ कोर्स दे कुड बी इक्वल, and in this example also you have one max pattern and two close pattern. But let's say if you wanted to find all frequent patterns, then you can think of I1 भी frequent है as a single item, I2 भी frequent है, I100 भी frequent है, I1 I2 भी frequent है, I1 I2 I3 भी frequent है, I1 I10 भी frequent है. So there are tons of them. ठीक है? So oftentimes we restrict ourselves to just close patterns when we are generating item sets, frequent item sets, and they give you a fairly complete picture of the knowledge from your data set. Okay.
सर
जी जी.
सर लास्ट एग्जांपल से क्वेश्चन है.
फिर से बताएं, मुझे समझ नहीं आई.
सर लास्ट क्वेश्चन से लास्ट एग्जांपल से क्वेश्चन है मेरा.
जी जी पूछें.
सर क्लोज आइटम सेट में दो वो एग्जांपल लिखी थी, लेकिन वो A1 to A100 क्लोज आइटम सेट कैसे हुआ?
A1 A100 क्लोज किस तरह हुआ?
यस सर, उसका तो सुपर सेट नहीं है, एग्जिस्ट नहीं करता जो कि सपोर्ट उससे कम हो.
So there exists no super pattern. तो basically कोई super pattern है नहीं with that condition.
तो फिर हम कैसे करेंगे कि क्लोज है, क्लोज आइटम सेट है?
uh,
क्योंकि उसके लिए एग्जिस्ट करना लाजमी है ना कि सुपर पैटर्न सुपर सेट हो आइटम सेट के
नहीं,
लिए.
उसमें वही है कि if doesn't exist it means that there is no super pattern. तो वो तो मतलब इन ए वे खत्म हो जाएगा ना, वो दूसरी कंडीशन पे अप्लाई ही नहीं होगी कि काउंट हमने देखना है कि नहीं देखना. देयर इजंट एनी सुपर पैटर्न. सो इन दिस सेंस आप जो भी आपका लास्ट लॉन्गेस्ट लेंथ का जो आइटम सेट निकलेगा आपके, दैट वुड ऑलवेज बी ए मैक्स पैटर्न और ए क्लोज पैटर्न.
ओके.
ठीक है ना? बिकॉज
ठीक
उसका
है.
सुपर पैटर्न तो है ही नहीं.
हम्म.
ठीक है? तो ये दिस इज इंक्लूडेड इन डेफिनेशन. ठीक है, वो शायद टेक्निकली इतनी वो स्ट्रिक्ट डेफिनेशन नहीं लिखी होगी, बट दिस इज मतलब this is the understanding कि if there is no super pattern, so then it's still a itself it has to be frequent, and there is no super pattern, then it's going to be a closed pattern or max pattern or both.
इटसेल्फ फ्रीक्वेंट हो.
हाँ, वो तो होना जरूरी है. वो
ठीक
तो
है.
दोनों की कंडीशन है, वो खुद ही भी फ्रीक्वेंट होना चाहिए. So in other words, हम स्टार्ट वहीं से करेंगे. Let's say if you wanted to find closed pattern or max patterns, you start from the set of all frequent patterns. ठीक है? जैसे जो ए प्रायरी या एफपी ग्रोथ एल्गोरिथम निकालता है, वो वहां से स्टार्ट करेंगे, उसमें से फिर फिल्टर करेंगे यूजिंग दिस कंडीशंस. एंड जो लॉन्गेस्ट आपको निकलेगा और जिसका सुपर पैटर्न है नहीं, वो डेफिनेटली होगा सी में और एम में। ठीक है, एंड एक्चुअली दिस इज जो लॉन्गेस्ट की आपने बात की है ना, दिस इज एक्चुअली अनदर इंटरेस्टिंग थिंग। तो फॉर सम एप्लीकेशन दे से ओके आई जस्ट वांट द लॉन्गेस्ट आइटम सेट, मुझे पता चलेगा कौन सी सबसे बड़ी कॉम्बिनेशन है, दैट इज द फ्रीक्वेंट। जैसे आप इफ यू टॉक अबाउट मार्केट बास्केट एनालिसिस, वी वांट टू से कि क्या व्हाट इज द लॉन्गेस्ट set of items that people buy together and is still frequent. So that would reduce it to just one or maybe a few item sets. So you can say that is even in general smaller than C, M, and F. ठीक है, is that clear?
Yes, sir.
So you can, I'll just mention this and maybe you can look at it at your own time. So remember, we are generating lots of pieces of knowledge. What are our pieces of knowledge? Our frequent item sets and our association rules. I mentioned association rules, I think a couple of lectures back, how you generate association rules from item sets. So, so we need to have nice ways of visualizing them. And people have come up with some ways, and some of those ways visuals are shown in these slides. Uh, Although they are not very perfect, but they might give you a quick idea of what's frequent and what's not frequent. Maybe you can have a 2D grid. एक साइड के ग्रिड में आपके पास लेफ्ट हैंड साइड है रूल का, दूसरी हैंड पे राइट हैंड साइड है, जहां उसकी इंटरसेक्शन बनती है वहां इफ दैट इज फ्रीक्वेंट यू हैव अ बार, द हाइट ऑफ द बार वुड गिव यू फॉर एग्जांपल द कॉन्फिडेंस। सो इस तरह करके कुछ लोगों ने बनाए हुए हैं। सम यूज ए ग्राफ स्ट्रक्चर टू यूज to kind of identify uh, rules as well as item sets that are frequent so that you can visualize them quickly. So you can look at these at your own time. So this is about the ball form of representation. All right. Any questions? Oops, ये क्या हुआ? All right. Okay, so the next topic that we wanted to talk about briefly is sequential pattern mining. So far we had talked about item set mining, set, not sequence. So set is of course distinct items, but their order is not important. So if order is important, uh, then we move on to what is known as the sequential pattern mining. And sequential pattern mining has many applications. Again, just like item set mining has tons of applications. So you can think of, for example, uh, trying to understand the behavior of users on your website. So maybe you have a website with multiple pages. Maybe the home page is A, then you have many other pages B, C, D, E. So you would like to analyze which sequence of pages people use, people visit. So do they come to A, then go to C, then go to D, then come back to A? So this is a sequence. Or maybe they don't even go to your home page. They might start from B, C, D, then maybe go back to your home page. So we would like to find such sequences that are frequent. Okay? So that's the idea behind frequent item set mining. Of course, it also occurs in the retail sector as well. And of course, in many other sectors. For example, let's talk about customer one. Customer one goes to the store one day, and buys, let's say, A and B, then goes to a store another day and then buys, let's say, A and C, then goes to a store again, let's say, another day and buy, let's say, C and D and let's say E. So now for this customer, this is a sequence. So what is a sequence? First A and B, and then A and C, and then C and D and E. Within that sequence, there would be sets or combinations, but those sequences are ordered. You cannot say that C, D, E occurs first and then A, B, and then so you cannot rearrange that. That ordering is fixed. And then based on this, you would like to maybe decide if someone bought, let's say, A and B, let's say A and B might be a printer and toner, then that person comes back and buy a toner again, and C might be, let's say, paper. ठीक है? So we like to see such trend कि एक चीज उसने एक दिन खरीदी है, next time वो क्या खरीदेगा. Similarly, for the web pages, what is the common order in which people visit a particular website? For example, you can even do this for textual content. So in writings, how do people write? So what words are used in sequence most frequently? So for example, Lahore University of Management Sciences. So this set of sequence of words would occur with some degree of frequency, as opposed to, let's say, Lahore uh, Sciences University. So this would occur less frequently. So it has applications in many places, even in bioinformatics as well. Biological sequences, which biological sequences occur frequently? Again, they are ordered. Okay. So the interesting thing is the algorithms that work on sequential patterns are very similar to those that work on item sets. And we will only study one algorithm which is very similar to the a priori algorithm, which is called the generalized sequential pattern. Very generalized name, actually. Okay. So this is very similar to a priori, so we will discuss this as well. There are also extensions to the FP growth algorithm for sequential pattern mining, which is, by the way, called prefix span. We will not discuss that in this course. So okay, before we start, we have to kind of be more precise with our notation as well as with our definition. So we said that we are talking about sequences. So S is a sequence, let's say. Okay. So we will denote a sequence as an ordered list of item sets. So, and sets are denoted in written in braces, or I would just say that I will write the brace later on. So let's say item set. Let me start more formally. So as before, we have I is the set of all possible items. ठीक है ना? So जैसे I1, I2, I3 to IM. So this is like आपके वेब पेजेस कौन से हैं, A, B, C, D है, या आपके words कौन से हैं. So this is the possible items that can occur in a sequence. ठीक है? And then you can have various sets of these. So for example, any set X, let's say I, would be in general a subset or equal to I. ठीक है? So then a sequence in general would be X1, X2, X3, and so on. So this is a sequence. So the ordering X1, X2, X3, and so on is fixed. That's not cannot change. Within X1, X2, X3, those would be items from I, and they could be any items and those items may repeat. So for example, let's say मैं कहता हूँ I, A, B और C है. So then this is a valid sequence, let's say. So for example, A, B, B, C. So this is a valid sequence. So you have 3 sets in it. And these 3 sets are, the first set is A, the second is AB, I think. So AB, and the third is BC. Okay. But you notice that in any particular sequence, the items may repeat, but they cannot repeat within an item set. So that's why we call them a set. Okay. Of course, if you talk about the web page problem, उसमें obviously एक वक्त पे एक ही पेज पे हम जाएंगे, तो वो set हमेशा single item का ही होगा. But in general, a set can have multiple items. ठीक है. So different applications के लिए sets बड़े भी हो सकते हैं. जैसे retail store के लिए एक set is one basket that is carried out. So for example, you can think of a customer who came to the store and bought A once, then the next day he bought A and B, and then some days later he bought B and C. So this is a sequence for that customer. Okay. Okay, now, so this sequence, the sets in it, the number of item sets, and sometimes they're also called elements or elements, is the size of the sequence. Okay. So what is the size of this? So size of S is basically then 3. There are 3 item sets in this sequence. So that's one definition or one concept. Secondly, now of items in a sequence is the length of the sequence. Okay. So ये size तो इसका 3 था, इसका length क्या है? So we have A, we have AB, and we have BC. So 4, 5. So length of S is basically 5. So in this, when we are talking about length, we count all items, and there may be repeated items in it. But of course, within an item set or element, there are no repeated items, because that's why it's a set. Okay. So S, the length of S is 5. So we also sometimes call this as a 5 sequence. Remember, we use the notation 5 item set, or in general K item set. So this is the same analogous, you can say, term for sequences. 5 sequence means that a sequence that has 5 items in it. So those items, of course, may repeat in multiple item sets, but overall they are 5 items. Okay, so with that, I mean, you understand what a sequence is formally. The second thing that we need to understand is what is a subsequence and supersequence. Okay? So just like subset and superset, so we need to know what is a subsequence and a supersequence. So let's take 2 sequences, S1 and S2. Okay? Let me write them here. By the way, generalized sequential pattern mining is not, I think, not available in both of your books. So I'm covering this section from another book called Web Data Mining, and I've placed the chapter of this book in the resources section of your LMS. Okay? चैप्टर 2 है, चैप्टर 2 का 2.7 है टू बी प्रिसाइज। सो ये वहाँ से आप पढ़ सकते हैं। ऑफ कोर्स यू कैन आल्सो फाइंड इट ऑन द वेब। So let's say, let me write an S1. So sequence, और हमने एंगल ब्रैकेट से एंगल, यू कैन कॉल इट ब्रैकेट या लेस देन और ग्रेटर देन सिंबल से डिनोट किया हुआ है। ठीक है, सो लेट्स से वी हैव अ सीक्वेंस ए एंड लेट्स से ए बी, छोटा लेते हैं अभी जस्ट टू अंडरस्टैंड। लेट्स से S2 हमारे पास है। ठीक है, सो ए बी एंड देन ऊपर क्या था? ठीक है, लेट्स से ए बी सी। So this is, in this case, S1 is a subsequence of S2. So how do we check for this? So let me just explain this. So you look at the first sequence, which is supposed to be or is likely to be the subsequence of the second, and look at its item one by one, item sets one by one by one. ठीक है? So the first item set is AB. Now you go to the second sequence and see that ये जो AB है second sequence में किस item set का subset है या equal है, and you start again from the second sequence from start. Order आपने देखना है, तो आप second sequence में देखेंगे तो it is a subset of the first item set or element which is ABC. ये भी AB है। अच्छा, ठीक है, तो पहले S1 का A था सिर्फ। So A is, if you take S1 का पहला element which is A, you check which element of S2 it is a subset or equal. You notice that it is a subset of the first element. इसका मतलब है कि हमने पहला element S1 का consume कर लिया, यूज हो गया। ठीक है, फिर हम दूसरा देखेंगे। दूसरा हम ए बी देखेंगे, जो पहला वाला हमने कंज्यूम कर लिया, तो पहला वाला किस में कंज्यूम हुआ है वो भी हमने कट कर देना है। वी वुड चेक विद ए बी। सो ए बी, द नेक्स्ट वन वुड बी चेक्ड विद द नेक्स्ट item set in order in S2, and we notice that AB is a subset of ABC. So इसका मतलब है कि जब दोनों कंज्यूम हो गए हैं S1 के in S2, then it means that S1 is a subsequence of S2, and they could be in they have to be in order. So let's say मेरा S2 जो था, let's say बीच में कोई और मेरे पास आइटम सेट है, let's say C D E. Here then again S1 is a subset of S2 because S1 का जो A था वो AB में कंज्यूम हो गया, AB था वो ABC में कंज्यूम हुआ, बीच में हमने एक स्किप कर दिया, उसमें कंज्यूम नहीं हो रहा था, बट ऑर्डर में हो रहा है कंज्यूम, और दोनों कंज्यूम हो गए S1 के, तो इसका मतलब है कि सारे कंज्यूम हो गए S1 के, इसका मतलब इट्स अ सबसेट। बट उसमें अब ये है कि नेक्स्ट टाइम लेट्स से S1 में कोई और आइटम सेट आगे होता, लेट्स से यहाँ मेरे पास एक आइटम सेट होता है C। ठीक है, मैंने ऑर्डर पे ही जाना है। आई चेक A इज अ सबसेट ऑफ AB इज अ सबसेट ऑफ ABC। C को सबसेट बनाना है एनीथिंग दैट कम्स आफ्टर ABC, and nothing comes after ABC, so it means that S1 is not a subsequence of S2. जो बीच में मिस हो गया वो मिस हो गया, we don't go back and check because that would break the sequence. ठीक है, so this last example S1 is not a subsequence of S2. ठीक है, is this point clear? ठीक है, so essentially जी क्वेश्चन पूछे।
Sir, can you repeat the point about this not being a subsequence?
हाँ जी, तो हमने
हाँ।
S1 को लिया, S1 का पहला एलिमेंट लिया विच इज A, और हमने S2 से कुछ शुरू किया, तो A हमने देखा किधर का सबसेट बन रहा है, A इज अ सबसेट ऑफ AB। इसका मतलब A कंज्यूम हो गया और AB से हम आगे जाएंगे सेकंड ट्रांजैक्शन में। अब हमने A कंज्यूम कर लिया, अब सेकंड एलिमेंट में गए S1 के विच इज AB हमने देखा कि CDC का तो सबसेट है नहीं, तो वो तो स्किप हो गया, ठीक है। फिर हमने देखा कि वो ABC का सबसीक्वेंस सबसेट है कि नहीं है, सो इट इज़ अ सबसेट, जिसका मतलब है कि AB भी कंज्यूम हो गया और हम थर्ड एलिमेंट पे पहुंच गए हैं S2 में। बट अब S1 में एक और एलिमेंट भी है C। अब C का जो हम सबसेट जिसका ढूंढेंगे वो ABC से आगे ढूंढेंगे, आगे कोई नहीं है, तो इसका मतलब है C किसी का सबसेट नहीं बन रहा, तो इसका मतलब है कि S1 इज नॉट ए सब सीक्वेंस ऑफ S2।
ठीक है, ओके सर।
ठीक है, यू गॉट
सर
दैट जी।
अगर S2 में A होता तो A से मैच हो सकता था, या
हाँ,
फिर
ए हो
सबसेट
सकता है, इक्वल
हो
भी,
सकता
इक्वल भी
है।
अलाउड है जी।
ठीक।
ठीक है, ठीक है, सो बेसिकली ये मेन कॉन्सेप्ट्स हैं। देन वी मूव ऑन, briefly discuss the GSP algorithm. As I said, GSP algorithm is very similar to the a priori algorithm. It's a level by level uh, candidate generation and test approach. ठीक है, but of course uh, we are now dealing with sequences, and the database that we're working on is a sequence database, not a transactional database. So उसमें आपके पास sequences हैं। For example, पहला sequence है, कुछ भी हो सकता है, let's say AB है, ठीक है। दूसरा sequence let's say CD AB A, ठीक है, and 3 so on, ठीक है ना। तो इस तरह के sequences हैं आपके पास। Within an element, the items are sets. So each element is a set and the items are written in some fixed order, जैसे हम a priori में भी करते थे। So कोई ऑर्डर आप फिक्स कर लें, उसी में ही लिखेंगे, A पहले होगा, B बाद में होगा, C बाद में होगा, ठीक है ना। बट इन ए सीक्वेंस ऑफ कोर्स they might be repeated items. So this is a sequential database. The whole idea in sequential pattern mining is find sequences that occur frequently, right? Which means that their support of that sequence should be greater than min support. ठीक है, greater than or equal to, ठीक है। सो ये वही डेफिनेशन है जो स्टैंडर्ड फ्रीक्वेंट आइटम सेट्स के लिए भी है और यहाँ सीक्वेंसेस के लिए। So how does the GSP algorithm works? Very similarly, but there is one difference which we will discuss. So we will generate one sequences and count them. So one sequence is essentially क्या होगा? So one sequence is जब मैं कहता हूँ one sequence has one item in it, not one element. K sequence का मतलब one K item. So when we say one sequence, so it's essentially A, ठीक है, B, C, तो सारे आइटम्स के आपका वन वन आइटम का सीक्वेंस बन जाएगा। सो यू काउंट दैम इन द डेटाबेस, यू गेट अ काउंट। इफ द मिनिमम काउंट इज लेस than minimum support, they get deleted. So from here you then generate the two sequences, candidate two sequences. So candidate 2 sequences from one sequences are something like this. So A and B, ठीक है, ये generate होगा as well as A and B, and as well as since this is sequences, you also generate, उल्टा भी generate हो जाएगा, B A, ठीक है. So candidates बेतहाशा generate होते हैं in sequential pattern mining, at least the GSP algorithm. Of course, this is not okay. So why is this not okay? BA in one set, because this is a set, और set में हमने कहा था item sets का order is not important, and we always write that item set in lexicographic order. So this is similar to or same as this one, ठीक है, ये दोनों same है. So we will not generate this, ठीक है. So we generate basically by joining two candidate frequent one item sets to generate candidate two item sets, and we generate them as A, B as separate elements, A, B as same element, as well as B, A as separate elements, B coming first. And then of course you will see many combination, A B के साथ किया, A C के साथ भी होगा, A D के साथ भी होगा, and so on. So this is for C2, but C2 से आगे थोड़ा सा और भी complexity है. So one point that we need to keep in mind is जो भी आपने next candidate generate किया, it has to be for sure a super sequence. ये item set में भी हम ये condition होती थी हमारी. By the way, अब यहाँ देखें जो BA है, it's a super sequence of A. So for example, so let's say B. So ये A का super sequence है. A जब लेंगे तो B के साथ तो मैच नहीं हो रहा है, but second item A के साथ हो रहा है. Similarly, this is super sequence of B. B के साथ करेंगे तो B के साथ हो रहा है, ठीक है. So it is a super sequence. Similarly, आप जो लेंगे ये वाला कट्ठा A B, इसमें भी A इसमें कंज्यूम हो रहा है, B भी इसमें कंज्यूम हो रहा है. इट्स ए सुपर सीक्वेंस. जिन दो सीक्वेंस से एक सुपर सीक्वेंस बना रहे हैं, इट मस्ट बी मतलब इट मस्ट बी हैव ए सुपर सीक्वेंस सब सीक्वेंस रिलेशनशिप. सो ये जनरेशन में इंपॉर्टेंट है, और ये आइटम सेट में भी हमने फॉलो किया था, ठीक है. तो बट हायर ऑर्डर में थोड़ा सा आपको फिर देखना पड़ेगा. उसका रूल जो जो यूज करते हैं वो ये है कि लेट्स से वी हैव टू सीक्वेंस S1 एंड S2, ठीक है. So what we do is in S1, so for example, remove, or you can say delete first item, not element, in S1, and last item in S2. If what is remaining is exactly the same, meaning that if you remove the first item from S1 and if you remove the last item from S2, if you get the same sequence after that, then they can be joined. And the new sequence would be, so new sequence, let's say S3, will be S1, S1 plus last item of S2, or I would say or and both generate होंगे. Okay, और ही होगा. सो S1 पूरा आपने लिख लिया, जो लास्ट आइटम था S2 का, इफ दैट वाज अ सेपरेट एलिमेंट तो यहाँ आप सेपरेट एलिमेंट ऐड करेंगे. इट वाज द सेम एलिमेंट, it would be added to same element. So let's take a quick example. I know this is sometimes confusing. Let's take an example. Let's say 3 item sets बनाते हैं. Let's say A, B, or let's say C. ये S1 है और इसका जब हम A निकाल लेंगे तो it has to be B और C. ठीक है, B, C and let's say D. ठीक है. तो पहले सीक्वेंस का A मैंने रिमूव कर दिया. So what I have is B, C. B as a separate element, C as a separate element. So exactly, if you remove the last item of second item, so if you remove the second item of so you get B, मैं लिखा नहीं है, एक सेकंड क्या हो रहा है, B brace left brace C, so B C एंड D. ठीक है, तो D हमने निकाल दिया, तो B एंड C भी, यहाँ भी 2 एलिमेंट बनेंगे, B और C, ऊपर भी B एंड C. तो इसका मतलब है दोनों कैन बी जॉइंड एंड दे विल गिव यू this first sequence. So C, look at C, जो second sequence में, was it part of its element or was it separate? It was actually part of a sequence. So यहाँ भी हम last sequence में add कर देंगे. So this would be the new candidate generator, and you will notice that this would for sure be a super sequence of those 2 sequences. But let's say let me repeat this maybe. So let me take another example. So let's say D was a separate element. So then क्या होता, तो नए सीक्वेंस में D सेपरेट एलिमेंट ही होता. तो ये जो जनरेट होगा अब, सो ये D इधर आ जाएगा, सेपरेट होगा. इट शुड नॉट बी पार्ट ऑफ द लास्ट एलिमेंट ऑफ द न्यू सीक्वेंस. अगेन अभी आप चेक करें, दिस इज अ प्रॉपर सुपर सीक्वेंस ऑफ बोथ द प्रीवियस सीक्वेंसेस. ठीक है. So this is how we generate candidates, and then of course counting उसी तरह ही होती है जिस तरह a priori में होती है. Go through each sequence and find whether that sequence is present in that sequence in the transaction in the sequence database. If it does, you increase this count, and then also you check whether all its k-1 subsequences are present in the previous frequent sequences. If they are not, then it is pruned. And secondly, they will be pruned if their count is less than the minimum support count. And you proceed in this fashion until you reach the maximum length. So ये एक example है. I have uploaded this example on LMS. So you can do a dry run using this example of the GSP algorithm. ठीक है. So you have a sequence database, and then you have the process of finding candidate one item sets, frequent candidate one sequences, frequent one sequences, candidate two sequences, frequent two sequences, and so on. ठीक है. So I have placed this on LMS, so ये आप देख सकते हैं. And of course जो चैप्टर 2 है वेब डेटा माइनिंग का, जिसमें ये 2.7 सेक्शन है, वो भी आपको अपलोड कर दिया, वो भी देख सकते हैं. ठीक है, तो I think that is pretty much all. In the next lecture, then we will talk about some interestingness measures, which we don't have time to start today. And then after that, there are some extensions or variations of applications of item set mining problem. And then finally, constraint-based item set mining. So there are still maybe 1.5 lectures is left, or maybe even 2. Any questions? So any questions?
Excuse me, sir.
ठीक है, आज है Thursday. So do we have a quiz on Monday or Tuesday? Should we have a quiz on Tuesday? Or I'm skip कर दें, because at the end of next week we have the exam on Friday. Actually लोग भी बहुत थोड़े हैं अभी. I don't know.
Excuse me, sir.
ठीक है. So I think I will probably not take a quiz on Tuesday. And of course you should prepare for your midterm exam on Friday.